Okay guys, in this video we are going to introduce a very important number in all of mathematics, about as important as pi in terms of its importance. It is so important that we give it a name, like 3.14159 so on and so forth gets the letter pi as its name. We have a number that is Euler's number. It's named after a gentleman. I'm going to put his name up here just to see who's taking notes here. Leonard Euler. And so Leonard Euler, since it's his number, we tend to use the letter E to give him credit for this thing. But we would just say that this number E, it has a name. You'll want to highlight this right here. It is called the natural log base, or we just refer to it as the natural base. And so in a lot of applications, you're going to see that we have exponential functions where E is our base of our exponent, and that's fine. So what do we know about E? Well, here's what I want you to know about it. First of all, that is a non-repeating decimal that goes on forever and ever, or it has a non-repeating decimal that goes on forever and ever. And we tend to just abbreviate it here. So when we say E is approximately 2.718-ish here, that's what I want you to know. You need to know out to 3 decimal places always that E is 2.718. But we are often going to be in the practice of using 2.71828, blah, 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 as our base. And so shorthand, we're not going to write 2.718-ish. We're going to use the exact value. We're just going to say E to the power of x here. So first things first, what I want you to find is on your graphing calculator here, we need to find our E to the power of button. So you're going to notice that there's this button that says ln, and that is actually our natural log key. Right behind the natural log key it says E to the power of x. E to the power of x is the inverse of a natural log thing, so they tend to put those things behind each other, just like we put squared and square root next to one another. So let's take a look at this right here. It says use a calculator to evaluate f of x equals e to the x for the given values of x. So since we're doing some evaluating here, I just say we're just going to build a table, x, f of x. And so we're going to plug in, it looks like, a few values here. I want to go left to right. So let's start with this, negative 7.1. And then I suppose the next x value on the number line would be negative 0.4, and then we would have positive 6.2. But the way this works is just like you think it would. We just take e to the power of negative 7.1. We're going to take e to the power of negative 0.4. We're also going to take e to the power of 6.2. So why are we doing this? Well, one reason is just to get you used to this idea that e is just some 2.718. It's some base, and we're raising it to a power like anything else. But another reason why is to get you to be able to find this on your calculator here. So we're going to say e to the power of negative 7.1. I'm going to go ahead and roll through all of these here. So I'm going to say again e to the power of, so second ln, and we're going to say negative 0.4. And then we're also going to get second ln, or natural base, to the power of 6.2. Whoops, 6.2. So with respect to the outputs we're getting here, it looks like on this first one we get 8.25 e negative 4. What? So first things first, what we mean by 8.25-ish e to the negative 4 is we mean 8.25 times 10 to the negative 4. So because we are going to be getting significantly smaller answers here, it's worth mentioning this one here, that we're not going to put on this table in scientific notation. We're going to have to say that this is the same thing as 8.25. I'm going to take the decimal out here, and we need to scooch that decimal back 4 times. And so this means that we have to fill in 3 zeros here. I'm going to put a 0 before my decimal just to kind of indicate that it was there. But we get about 0.000825. And what I would say is, because I want to be very accurate with small numbers, let's put on the first 4 non-zero digits. So 8251. We want to always include the first non-zero digits, the first 4 non-zero digits. So what did we get when we took e to the negative 0.4? We got about 0.6703. So about 0.6703. We could probably get away with just doing 2 decimal places here because there weren't a lot of zeros there to precede it. And then e to the 6.2, what would happen if I took 2.7 times itself about 6.2 times? We get about a 492.75. 492.75. So e is just some natural base, and you need to know that it's about 2.718. But what I'd like to be able to do is also sketch graphs of exponential growth and decay using this natural base here, since we use it so often. So it says for each of the following, graph the parent function y equals e to the x in the coordinate plane, and then graph the transform function, being sure to label, sketch and label the horizontal asymptote. Okay, so we say e to the x. What does this look like? Well, the good news for you is that we're going to treat this the same way we do with a lot of our functions here, and that is to plug in -1, 0, and 1. And so in each of these instances, I get e to the 0, e to the 1, e to the 1, e to the -1 is more like it, and I get e to the 1 here. So some things. I know that e to the 0, I know that one. That's 1. And e to the 1, you know what? I would dare you to take e to the first power on your calculator, but what you're going to see is e to the first power is just this number 2.718-ish. So we're going to put, about 2.718 here. And then e to the -1, yeah, I don't know that one. So we're going to have to go back in and we'll say e to the -1 is the reciprocal of 2.718-ish, but we get about 0.37-ish. I'm going to say 0.368-ish. 0.368-ish. So with respect to what this looks like, my favorite thing to tell you is it still has a horizontal asymptote on the x-axis. All parent exponential functions do, and this is our parent exponential function with base e. It still goes through 0, 1. It still goes through 1 comma whatever the base was, just like we said here. 1 comma whatever the base is, and then -1 comma the reciprocal of that base. And so in this particular instance here, the reciprocal of 2.718 is about 0.368. So we're right here. All we want to know is that this graph kind of goes up and through here. And just to be thorough, maybe we'll put on e to the second here. E to the second, just to be clear, what would we get? It's about 7.389. So we get e to the second is about 7.389. I can see that that's, let's see, 3, 4, 5, 6, 7, and a little bit higher. This would be a very, very good sketch of our parent function with base e, or natural base. So how in the world would I ever expect to graph g of x here? Well, the fact is that it is just some transformation of our original parent function. And so when you look at how these transformations occur, it's really kind of a weird thing because we have to do them in order. I would have to do what's in parentheses first. So in other words, I have to shift all my points left twice. And then before I do this subtraction out here, I have to do my multiply by 2, which is really a vertical stretch by a factor of 2. Meaning that from this point 0, 1, I have to go left 2. And instead of being at a height of 1, now I'm at a height of double that. And then I have to take that and I have to shift it down 3. I feel that that's really, really complex. So what I'm going to do is I'm going to give you some advice. When it comes to graphing natural base exponential functions, I want you to make a table as well, but this is where we're really just going to play it safe and say, look, I know my graph was shifted left 2, so maybe I make my central x value here -2, but I'm also going to put in -3 and -1, and maybe I'll plug in 0 and I'll plug in -4, and we're just going to put our values into this. And so what we end up with here is 2e to the -2 plus 2 minus 3. And so I'm going to do this on my calculator here in a moment, but I want you to see we get 2e to the 0 minus 3, which is really, e to the 0 is 1. 2 times 1 minus 3, which is 2 minus 3 is, -1. So this is going to be good practice in a few things here. I get my calculator out. We're going to type in a skeleton expression. So if I said 2e to the power of -2 plus 2 in parenthesis minus 3, you're going to see we still get my -1. But what I want you to do is hit second enter. And what that's going to allow you to do is go back and just modify the statement that we just had here. And maybe we put in a -1. And so I notice that it's about 2.45-ish. So 2.45-ish. I'm not going to write ish on the rest of these. But if we plug in 0, I hit second enter, and I go back and I modify this, so I have to delete out my negative this time and then overwrite this with a 0, but I would get about 11.78. So 11.78-ish. When we plug in -3, I hit second enter. We're going to go back and make my 0. We're going to have to put in a negative. In this case, because I want to insert a 3, you have to hit second delete. This makes it into insert mode, and when I hit 3 this time, it's going to bump everything to the right. We get about -2.26, so -2.26-ish, and then when we plug in a -4, second enter, we'll go back and make our -3 and -4. We get about -2.73-ish, so -2.73-ish. So when it comes to sketching this transformation right here, what might this look like? Well, first things first, I do want to indicate something. Your asymptote would be shifted down 3 units. And so that's one of those things that I would tend to put on there first just to kind of give you your bearings here. We're going to label this y equals -3. But if I'm just plugging in points on my table here, this says I go left 4, 1, 2, 3, 4, down about 2.7. Left 3, down about 2.26. Left 2, down 1. Left 1 down, left 1 up 2.4-ish. So left 1 up 2.4-ish from the origin, be about a little less than 2.5. And then if we said 0, 11.78, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.78. That would put it somewhere up here. So when it comes to sketching natural base exponential functions, here's the rule. You still need to know how to find your asymptote using your k-value, but other than that, we're just going to table some values and make a sketch of it. And in terms of why I chose to table around -2, it's because I knew this graph had been shifted left 2. So we're going to hold off on sketching this one here just because we have a few other videos in which we're going to look at, I guess, decimals that you get in your exponent like this on a natural base expression. But that is how you would interpret the value of e as 2.718, and that's how we would sketch those graphs.